Electric dipole is formed by two equal and opposite charges q with separation b. The charges have same mass m, is kept uniform electric field q. If slightly rotated from its equilibrium orientation, then its angular frequency omega e. So we have this constant electric field lines, and in this constant electric field line, we have placed the dipole, and now we are disturbing the dipole, and then we have to find a stampede of a small oscillation. So it is said that the charges have same mass in it is kept uniform electric field. Okay, so this is basically the orientation uniform electric field. Now this dipole is slightly displaced from this position, okay, and released. So let's say if I displace the dipole by a small amount theta, okay, then the force that you see here on this side, the force will be QE, and on this side force will be QE, like this way. So these are the forces that will be acting on the dipole Q, and you can see that these two forces are acting like a couple, and its mass is m here. Now always remember that if the net force on the system is if you check net force on the system, that is 0 here, and in this scenario center of mass is not moving at all. So basically the center of mass, because acceleration of the center of mass is 0, net force on the system is 0, so the body will rotate about the center of mass. Now it has a mass of m here, and here also mass m is there, so center of mass will lie exactly at the middle point of this one. So if I calculate the torque, now listen, you can write the torque about any point, you will be getting the same value of torque, because torque due to couple force is independent about which point you are calculating. At all the points you are going to get the same value of torque. So if I calculate the torque here, let's say this is A and this is also A. So torque about O, if I write, that is restoring torque in nature. So restoring. Why I'm saying it restoring, you can clearly see that I had displaced the particle in this direction like this way by angle of theta here in this sense. But you can feel the sense of the restoring torque. It is trying to rotate it in opposite manner. That's why I said restoring torque. So this restoring torque will be written as QE into A, and this is theta, so this distance is basically A sine theta due to 1, and due to other force also same value QE A sine theta. So this we will be getting twice of QEA sine theta here, and then basically I will write Q into 2A times E sine theta. So this is PE sine theta here. This is restoring torque. So uh, you can see that if theta is small, then I can write torque equals to Pe theta, and then this torque restoring can be replaced with I about O into alpha, that is Pe theta. This is restoring, and alpha can be written as omega square theta, that is Pe theta here for SHM, angular SHM. So omega that we got here, that is under root of Pe by I naught. And what is the moment of inertia? So moment of inertia of the particle about the center of mass. Here masses are given. If the masses are not given, masses are not equal, then in that case I about cm, always remember you will be writing m1 m2 by m1 plus m2 into whatever the distance is basically 2a, so I will be writing 2a square. So this you can directly apply here. Surprisingly here both have the equal masses. So we will be writing ma square plus ma square, and so omega will be under root of Pe. Omega will be under root of PE by 2MA square. So this is the angular frequency root under PE by MA square. Now, if you see the option, it is said that a separation is D, so basically 2A is equals to D here, and P is written in terms of charge Q. So no problem, I will write P equals to, let's say that is Q into D, okay, and M, I will write 4A square divided by 2. So 4A square is nothing but that's a D square only, so this will become Q times D by 2M times D square. So D square and D will cancel, and definitely electrical is also there, so this will become 2QE by MD. That's the angular frequency root under 2QE by MD. So correct option is option 3 here.